Hello दोस्तों, I welcome you all in lecture for civil engineering. Basically, I have started a big video lecture series on civil engineering subjects. Today, I have started from a very basic topic of structural analysis or the strength of material, that is reaction, and I will start other subject as well. So today we will see a very basic, a very short topic of structural analysis, that is reaction. Okay, let's see. Let's start. Okay, now what is reaction? At first, what is reaction? What mean of reaction? Actually, the word reaction is made of re plus action, right? The reaction word is made of re plus action. But now what is mean of this? The mean of this is the reaction is something which resists the action. Okay, now in case of structural element or structural structure, what are the action? In case of structure or the structural element, actions may be shear force, bending moment, axial force. Okay, these are the action in case of structural element which are comes into the picture with with the external loading. External loading may be dead load, live load, another type of load such as earthquake load, uh, wind load, etc. Okay, now these are the action due to the external loading. Now how the reaction are generated in the structural element. Okay, now we will see how the reaction are generated in the structural element. Let's for example take a simple example of a simply supported beam like this. This is a simply supported beam like this with some arbitrary load W which is inclined. So due to this inclined load, this inclined load have two components, one in horizontal direction, one in vertical direction. Okay, due to this load W, we can see our, if I cut a section here, if I cut a section x here, if and I draw a free body diagram of this, now this beam at this section, our free body diagram will look like this. I am drawing the left part, one reaction here, and some axial force, some shear force, and some sort of bending moment. These are the action due to this load W. This is the shear force, this is the shear force, this is the axial force, this is the bending moment. Right, now how the reaction are developed to these actions, right? If our beam have to work properly, so our beam should develop an internal shear force and an internal bending moment and an internal axial force, which should be equal to the external axial force, external shear force, or external bending moment for the safe bearing of this external loading. Now how the these reactions will generate in our in this beam, like, okay, let's discuss first how the internal bending moment will generate in our beam for counterbalancing this external bending moment, right? You know, from our RCC, generally our beam has made of RCC. If I talk about the singly reinforced beam look like this. This is the beam, have some reinforcement in the tensile zone. This is the simply supported singly reinforced beam. We know it have some, it has some neutral axis here, right? And this neutral axis, you know, this neutral axis divide this RCC section in the tension and compression zone. We know this topmost zone will be compression zone. If you are not understanding this how it is happening, we will discuss separately about this. Now you should focus only how the internal bending moment is generating in case of singly supported beam. Now we know so this neutral axis dividing this cross section in the compression zone and the tensile zone. This is the above zone above the neutral axis is the compression zone, and the zone above the below the neutral axis is the tensile zone. So this is the compression zone, right? Compression, this is the compression zone, this is the compression zone, and this is the tensile zone, right? All this is separate, all this we will discuss separately in RCC also. So now and here we will discuss only how the internal bending moment is generating in our beam section, right? So now if I draw a stress diagram for this beam section, the stress diagram for beam section look like this. At the neutral axis, the stresses will be 0, and stresses will increase linearly from the neutral axis up to the topmost fiber of the compression zone, like this, right? This is the straight line, okay? And as well as the stress in tensile zone also will increase linearly from 0 to maximum to at the center of the RCC, sorry, reinforcement. In case of RCC, we consider uh, only tensile reinforcement is uh, bearing the total tensile load, and we neglect the effect of this concrete in the tensile zone. So now this is the our stress diagram, right? In stress diagram, we can see this is the maximum here. Here are the maximum compression stresses, and here are the maximum tensile stresses. Now we know, if I multiply the stress by the area, we will get the compression force. So the compression force will act like this here, like this. Let compression force C acting like this, and if I multiply the tensile force, sorry, tensile stress by the area of steel, then we will get a tensile force. These are the opposite to each other, because this is the compression and this is the tensile force. So now for balance section, our compression force should be equal to tensile force, and we know the distance between these two. So now these two, compression and tensile force, are making a couple like this. We know couple how this is generating a couple, right? These C and T are generating a couple like this. This is compression force, sorry, this is compression force, this is tensile force, and we know the distance between the center of CG of compression force and CG of tensile force is known as lever arm, which is denoted by Z. Like, this is the distance between the compression CG of compression force and CG of tensile force, which is known as lever arm. So now if we if we calculate the moment of this perpendicular distance between compression force and tensile force, is known as lever arm, which is represented by the Z. This is the Z. Now this is Z. Now if I calculate the bending moment generated by this couple, will be bending moment by this couple will be C into Z, or T into Z, which will be equal, because C is equal to T. Okay, compression force is equal to tensile force. So this is the internal bending moment generated due to this material property of this RCC beam section. So this is the internal bending moment. That means this is the internal reaction which will counterbalance the external bending moment due to external loading. So we have seen how the internal bending moment, or the internal resistance for the bending moment, is generating in our RCC beam in case of singly reinforced beam. Okay, now we have seen how the internal reactions are generated in the beam section, right? So now we will discuss where will be the reaction be generated. We have seen how the reaction are generating in the any structural elements. For example, we have seen how the internal bending moment, or the internal resistance for the external bending moment is generating in the RCC singly reinforced beam. Okay, now we will for and this is that for the this is for the bending moment, as well as you can see for the mm, shear force, how the internal shear force is generating, and how the internal axial force is generating. All these are reaction are generating by the material property of our structural element. Okay, now we'll discuss where will be the reaction will generated. Okay, so let's see. Uh, let I rub this first. Okay, now where will be the reaction is generated? Where will be the reaction will generated, right? Now where will the reaction will generated, at which point, which will resist the respective action, right? For example, let's take a simply supported beam. Let's take a simply supported beam like this. This is a simply supported beam, right? This is a simply supported beam, some arbitrary loading. Now where will be the reaction will generated? Okay, suppose that some inclined load. Okay, let's take an example of simply supported beam. Like, I have drawn simply supported beam like this, some arbitrary load, inclined load acting on this beam. So now if I cut a section here, like this, and I draw a free body diagram, so we can, if I draw a free body diagram for this beam, we have some axial force, some bending moment, and some shear force also, right? So now this section will resist all these axial force, bending moment, and shear force. So this section XX will generate internal reaction in form of axial force, in form of shear force and bending moment. But if I place roller, sorry, a hinge like this in this beam, this is a hinge. I have provided a hinge here. One second. This was simply supported beam, but I have provided a hinge here like this. Okay. I have provided a hinge like this. Now some arbitrary load acting on this beam. So now if I cut a section on this hinge x, we know, hinge have the property that it can't resist the bending moment. So if I draw a free body diagram at this hinge, now our free body diagram will look like this. This is the hinge support. There will be a horizontal reaction also, and only shear force and sorry, axial force and shear force. There will be no internal bending moment. So from this example we have seen at this hinge support or the pin joint, sorry, and this is pin joint. At this pin joint we can see our beam is not generating internal bending moment. So here will not our beam will not subjected to any bending moment. So there will be no internal bending moment. So there will be no internal resistance toward the external bending moment. So we have seen how the reaction is generating and where the reaction are generating. So now we will discuss type of the reaction and type of support. Okay, so I have prepared a slide here. Okay, so now we will see, we have seen what is reaction. Now we will see what type of the reaction. Basically reaction are two types. One is internal reaction and another is external reaction. Now what are the internal reactions? Internal reaction are nothing reaction generated within the member of the within the structural element is known as internal reaction. As we have seen previously, example of simply supported beam which was subjected to arbitrary load, we have cut a section like this, and we have drawn a free body diagram. From we have seen this beam look like this after free body diagram, some like this, some bending moment, axial force and some shear force also, right? So these are the internal reaction, the reaction developed for the counterbalancing these uh, actions. So for counterbalancing this bending moment, axial force and shear force, these are the internal reaction. So for we have various type of structure elements. So for example we have beam, for beam we have already discussed. Now we'll discuss for the internal reaction. For I have made a table here also. Internal reaction for trussage. So okay, so in case of I have made a truss here. In case of truss, we know for first we have some assumption for the truss calculation. In case of truss calculation, we have the very first assumption is all the joint of the truss are pin joint, and our truss elements are subjected to uh, only axial force. Either the axial force may be tension or the compression. Okay, and all loads are acting on the joint of the truss. These are the basic assumption of the truss uh, calculation or the truss analysis, right? So now in case of truss, we will see the internal reaction. If I cut a section like this, here I have cut it this section. If I cut a section like this, we can see we have uh, drawn a I have drawn a free body diagram. So in case of if I cut it section free body diagram, we will some here reaction, and we have axial force like this. So in case of axial force, there will be only one internal reaction which will be in form of axial force. If our external action in truss member is compression, then our internal or the counterbalancing action reaction will be tension. If our external action is tension, our internal reaction will be compression. Just reverse of that. Okay, so now this that all the internal reaction for the truss members, right? Okay, now we will discuss for the frames. I have drawn the frame. Frame is nothing. Frame is a combination of beam and column. You are familiar with this type of construction. So in case of if I cut a section, I have cutted a section here. Some suppose that this truss also acting some sort of load like this and like this, right? So due to this loading, if I cut a section here, any any member of the truss, sorry, frame, so we have seen we will get like beam, we will get some shear force, bending moment, and axial force. So these are the internal reaction in case of the truss members, like sorry, frame members. Okay, so I have prepared same table for same. So for this is for the internal reaction for the truss in case of 2D and 3D. In case of 2D, there will be one internal reaction, there will be axial force, and also one internal internal reaction in case of 3D also. Okay, so now in internal reaction for frame, there will be three internal reaction, that will be axial force, shear force, and bending moment. And in case of internal reaction in case of 3D frame, there will be six internal reactions. Okay, now that was the internal reaction. Now we will discuss the what are the external reaction. Okay, now what are the external reaction. Now we'll discuss about. Okay, this is the simply supported beam have subjected to some load W, inclined load. This W load have two component, and horizontal and vertical. So now this the vertical load will bear by these two support. Okay, if our beam have to work properly, so our beam should be safely beared by these two support. This is the hinge support and this is the roller support. Okay, now for safely bearing this vertical load, our support should develop vertical reaction like this. Okay, so where will be these vertical reaction will generated, and for safely bearing this horizontal load, our support should develop horizontal reaction just opposite to this horizontal load. uh, okay, so where will these vertical and horizontal load will generate will depend on the type of support. So let's discuss where will be the reaction and which at which support which type of reaction will generate it. Okay, so let's take first type of support and where will which type of reaction will generate at that type and that type of supports. Okay, so first let's take a hinge support. Hinge support is represented like this. Okay, like this. Okay, hinge support is represented like this, and this, for example, we have taken a hinged support. In case of hinged support, if this hinge support is subjected to a vertical load like this, then this hinged support dif- will not displace in vertical downward direction. So if our support will not allow the respective displacement due to external loading, then this support will develop reaction for that type of external action. In case of hinge support, we can see our hinge support will not displace in vertical direction, so there will some vertical reaction in case of hinge support. And as well as if our support is subjecting some horizontal load, so our hinge support has the property it will not allow the horizontal movement of this support, so there will be a horizontal reaction also. So in case of hinge support, we have two type of, and if our as well as our if this support is subjecting some external bending like this, so our hinge support have the property that it will permit the bending of this support, so there will no resistance toward the external bending moments, and so there will be no reaction toward the bending moment. So there will be only two support reaction that will be in one in horizontal direction, one in vertical direction, as I have mentioned here. In case of hinge support, we for 2D we have only two reaction that are the Rx and Ry, that means in vertical direction and in the horizontal direction, right? Rx means horizontal direction, Y means vertical direction. Okay, so in case of same as well as in case of 3D, hinge support have three support reaction that are the Rx, Ry, and Rz, and that means X direction, Y direction, and Z direction in case of 3D. So now we will discuss next type of support, that is roller support. Okay, roller support is represented like this. Sorry, roller support is represented like this. Okay, in case okay, now we will imagine a practical situation of roller support. We can take an example of ball of a ball of a plank which is placed over a ball on the floor like this. This is the ball, this is the ball, and a plank, this is a plank placed, this is the floor. Okay, okay, this is the ball which is placed over the floor and a plank is placed over the ball. If now this situation is resemble with the roller support. If now uh, mm, I apply a horizontal force on this plank which is parallel to the floor plane, then we can see our plank will move in the uh, plane which is parallel to this floor plane. Okay, so now our this roller support is permitting the horizontal motion, the horizontal movement of this plank. So this we can see from this example, our roller support is not resisting the movement of this support in horizontal plane, so there will be no horizontal reaction. But in case I apply a load on this plank like this, there will be no displacement in this floor. Okay, so uh, our roller support is providing only one reaction, which is in vertical direction. There will be no reaction generated in the horizontal direction, because our roller support is permitting the is allowing the movement in the horizontal direction, as we have seen in case of a plank is supported over the ball on the floor. Okay, now I have mentioned here, in case of 2D there will be only one reaction, and in case of 3D there will be only one reaction, that is Ry, and in case of 2D also there will be only one reaction, that is Ry. Next type of support is the next type of support is that is sorry the next type of support is the next type of support is fixed support. Fixed support is represented like this. Fixed support means inbuilt support, right? Inbuilt support. Okay, next support is fixed support. Fixed fixed support. Okay, the next support is fixed support. Fixed support, right? Fixed support is represented like this. Okay, fixed support is represented like this. In case of fixed support, we can see our fixed support is not allowing any vertical movement, any horizontal movement, and not allowing the bending of this member. So our fixed support is generating, in case of 2D, three support reactions, that are the Fx, Fx, Fy, and Mxy in case of 2D. And in case of 3D, our fixed support will generate six reactions, that are the Fx, Fy, Fz, as I have mentioned here also. As I have mentioned here, in case of fixed support there will be three reactions: Rx, Ry, Mxy. In case of 2D, 3D, there will be Rx, Ry, Rz, Mxy, Mzx, Mzy. These are the six support reactions in case of fixed support. Okay, now next type of support is the roller support. Okay, roller support. Next type of support is the roller support. Roller support look like this. Roller support look like this. Okay, in case of roller support, roller support have the property, it allow the vertical displacement of this support, and will not allow it will support vertical movement, it will allow vertical movement, but it will not allow the horizontal movement, and it will not allow bending also. So in case of guided roller, we have two support reactions, that are the Fx, right, then Mx. This is the these are the guided support. Okay, so that was the reaction. So I will come with another lecture. It was my first lecture, so I will improve the quality. So thank you.